All right, today we're going fundamental, like really fundamental. We're going to talk about the particles that literally carry the forces of nature, the invisible messengers that tell all the matter in the universe how to behave. So yeah, let's dive in and break down exactly what a boson is.
It's maybe the biggest question we've ever asked. And when you zoom way, way down, past the molecules, past the atoms, all the way past protons and neutrons, you find this hidden world that's run by just a handful of truly elementary particles. These are the absolute rock-bottom ingredients of everything.
And it turns out these ingredients really only come in two main flavors. On one side, you've got the fermions. A good way to think of these is as the bricks of the universe. The quarks that build protons, the electrons that orbit them. They're the particles of matter. But on the other side, you've got the bosons. And they're not the bricks, they're more like the messages being passed between the bricks, telling them what to do. They're the particles of interaction, the force carriers.
So, what is it that makes a particle a boson? Well, it all comes down to some really specific, and let's be honest, pretty weird quantum properties.
Okay, so here's the textbook definition for you. A boson is a particle that mediates the fundamental forces, but the really critical thing that defines them is something called spin. Now, this isn't like a tiny spinning top. It's a deep, built-in quantum property. And for bosons, that spin value is always a whole number, 0, 1, 2, and so on. And that little detail, that integer spin, that's the key to everything they do.
And this is where it gets really interesting. Because of that integer spin, bosons are what you could call social particles. They follow these rules called Bose-Einstein statistics, which basically means they have zero problems sharing their space. In fact, they love it. You can have countless bosons all piled into the exact same quantum state, in the same place, at the same time. This is something that's totally forbidden for those antisocial matter particles like electrons. This whole clumping together thing is actually what makes technologies like lasers possible. It's just trillions of photons all moving in perfect lockstep.
To really get a handle on bosons, let's just start with the one that you interact with every single second of every day, the photon, the particle of light itself. Man, our understanding of light has been such a wild ride. For most of the 1800s, scientists were totally convinced light was a wave. I mean, all the experiments pointed that way, and Maxwell's amazing work even unified it all into his theory of electromagnetism. But then some problems started popping up. At the start of the new century, Max Planck realized he could only make his equations work if energy came in these little discrete packets, or quanta. A few years after that, Einstein took it to the next level, suggesting that light itself is made of these light quanta. It was the only way to explain how light could knock electrons off a piece of metal. But it wasn't until 1926 that these little packets of light finally got their official name, photons.
So what is a photon exactly? Well, it's a boson with a spin of 1. It has absolutely no mass and no electric charge, which means it can travel at the ultimate cosmic speed limit, the speed of light. Its whole job is to be the messenger for the electromagnetic force, carrying that message for everything from a magnet sticking to your fridge to the sunlight hitting your face.
So now that we've met the photon we all know and love, let's move on to its much stronger and, frankly, much stranger cousin, the gluon.
The name really tells you everything you need to know. When the physicist Murray Gell-Mann first came up with the idea for this particle back in '62, he called it the gluon, for a super simple reason. He pictured it acting like some kind of cosmic glue. And that's precisely what it does. Gluons are the bosons that carry the strong nuclear force, which is by far the most powerful force in the entire universe. Their whole purpose is to bind these fundamental particles called quarks together, locking them up tight inside the protons and neutrons that make up the nucleus of every single atom. I mean, without gluons, atomic nuclei would just instantly fly apart. All the matter we know would just poof.
Okay, so this is where gluons get really weird. For electromagnetism, you've just got one force carrier, the photon. Nice and simple. But for the strong force, there isn't just one gluon. There are 8 of them. So why the complication? What's going on?
The answer lies in a property that has absolutely nothing to do with visual color, but physicists playfully call it color charge. So while electric charge just comes in positive or negative, the strong force's color charge comes in 3 types: red, green, and blue. And a gluon's job is to change the color of a quark. So to do that, it has to carry both a color and an anticolor itself. So let's do the math here. If you've got 3 colors and 3 anticolors, you can make 9 possible combinations, right? You could have a red anti-red or a red anti-green, a green anti-blue, and so on. So why don't we have 9 gluons?
Well, it turns out there's a catch. One very specific combination, a perfect mix of red anti-red, green anti-green, and blue anti-blue, ends up being perfectly colorless. It's what's called a color singlet state. And because the whole point of the strong force is to exchange color, a messenger that is itself colorless just can't do the job. It's completely unable to carry the strong force message.
So you take your 9 mathematical possibilities, you subtract the one combination that's useless, and what are you left with? Exactly 8 independent, color-carrying types of gluons. It's a really cool example of how the beautiful, and yeah, sometimes tricky, math of particle physics plays out in reality.
But the gluon has one last trick up its sleeve. It's a feature so powerful and so strange that it gets its own special name, confinement.
And here's why this is so completely bizarre. Every other force we know, gravity, electromagnetism, it gets weaker with distance. You pull 2 magnets apart, their attraction fades. But the strong force does the exact opposite. It gets stronger. The farther you try to pull 2 quarks apart, the harder the gluons pull them back together. It's like they're connected by a cosmic rubber band that just gets tighter and tighter the more you stretch it. And if you pull hard enough, the band doesn't break. Instead, it becomes easier for the universe to just create a new quark and antiquark pair out of pure energy. The end result? You can never, ever find a quark or a gluon all by itself. They are forever trapped or confined inside larger particles.
So we've met the massless photon and the incredibly powerful gluons, but that doesn't complete the family picture. There are 2 more fundamental forces in what we call the standard model, and you better believe they have their own boson messengers. So let's meet the rest of the zoo.
First up, you've got the heavy W and Z bosons. These guys are the messengers of the weak nuclear force. And don't let that name fool you, this force is absolutely essential. It's what allows the sun to fuse hydrogen into helium, which powers our star and pretty much every star in the sky. And then, of course, there's the celebrity of the group, the Higgs boson. It's a really unique one. Think of it less like a messenger and more like part of a cosmic molasses that fills all of space. And as other particles try to move through this field, they get a bit of resistance, some drag. And that resistance? That's what we feel as mass. Without the Higgs, everything would be massless, just zipping around at the speed of light, and atoms could never form.
So we spend billions of dollars building these massive colliders to smash particles together just to find these exotic bosons. And it's a totally fair question to ask why. Why does any of this matter to our actual everyday lives? The answer is that the pursuit of this kind of fundamental knowledge has always paid us back in ways that nobody could have predicted. The goal isn't to build a better toaster. The goal is to understand the universe. But in the process of building the crazy tools you need to do that, you accidentally invent the future.
I mean, the technology we had to develop for particle physics has given us things like the powerful superconducting magnets in every MRI machine, and huge advances in the kind of computing that powers massive data networks. And, oh yeah, the next time you browse a website, just remember that the World Wide Web itself was invented at CERN. Why? For a really simple reason. Physicists just needed a better way to share their data about all these particles.
So, bosons are the messengers of the universe. They carry the fundamental rules that shape all of reality. And we've gotten pretty good at reading some of their messages, but we know for a fact there are still huge mysteries out there, things like dark matter and dark energy, that they might hold the key to. The search for answers is still going, which kind of leaves us with one final thought. We've found the messengers, but what secret messages have they yet to tell us?
Welcome back. Today, we're going small. Like really, really small. We're going to talk about the unsung hero of the universe, the particle that's basically the cosmos' strongest superglue. We are talking about the gluon.
All right, let's kick things off with a huge puzzle. Think about basic physics for a second. What do like charges do? They repel, right? So, how in the world does the core of an atom even exist? It's crammed full of positively charged protons that should be pushing each other apart with incredible force. Why doesn't it just, explode? Something unbelievably strong must be holding it all together.
And that's where our particle of the day comes in, the gluon. Seriously, that's its name. And it's no coincidence either. The name was cooked up by physicist Murray Gell-Mann way back in 1962 because that's exactly what it does. It is literally the glue holding the most fundamental bits of matter together.
So, To really get a handle on what these gluons are up to, we've got to zoom in, way, way in. We need to look inside the protons and neutrons themselves, the things that make up that atomic core. So what's on a gluon's to-do list? Well, first off, you need to know that protons and neutrons aren't the end of the line. They're actually made of even tinier things called quarks. And job number one for the gluon? Sticking those quarks together. By doing that, it's basically carrying or mediating the strong interaction. And trust me, it's called strong for a reason. It's the most powerful of the four fundamental forces, and that's the force that keeps the whole nucleus from flying apart. Okay, so this force works through a special kind of charge, but it's not the electric charge we're all used to. It's called color charge. Now, I have to say this right away. This has zero to do with red, green, or blue. Seriously. It's just a kind of playful name that physicists came up with for the property that quarks have. Think of it like positive and negative, but for quarks.
All right, let's explore this whole world of color, because how gluons deal with this charge is what makes the strong force so bizarre and so powerful.
So, to see just how unique this is, let's think about photons, the particles of light. Photons carry the electromagnetic force, but they don't have an electric charge themselves. It's like a delivery person who drops off a package but never opens it. Gluons? They're totally different. They actually carry the color charge of the very force they're responsible for. And that one little detail changes everything. Because gluons have this color charge, they can interact with each other. You know how two flashlight beams can pass right through one another? Photons don't interact. But gluons are constantly grabbing, pulling, and interacting with other gluons. This makes the whole thing a super complex, sticky mess of a force field. It's actually why the theory behind it, which is called quantum chromodynamics, is way, way harder than the physics of light and magnetism.
In fact, it gets even crazier. This whole self-interaction thing is so complicated that there isn't just one kind of gluon. Nope, there are 8 different types. 8. Each one has its own specific color and anticolor combo, and they all work in concert to hold matter together.
So, all this strange behavior leads to what is maybe the weirdest, most mind-bending property of the strong force. It's a phenomenon called quark confinement.
And that brings up a really obvious question, doesn't it? If a proton is just 3 quarks glued together, why can't we just, get some tiny tweezers and pull one out? I mean, it seems simple enough. Well, people have been trying for decades, and guess what? It's impossible. No one has ever managed to isolate a single quark.
And here's the absolutely wild reason why. You know how gravity and magnetism get weaker with distance, right? The farther away you are, the less you feel them. Well, the strong force doesn't play by those rules. It doesn't get weaker. Instead, as you try to pull 2 quarks apart, the gluon field between them snaps into this kind of flux tube. You can think of it like a cosmic rubber band. But here's the catch. This rubber band doesn't get weaker as you stretch it. The force stays constant. And the more you stretch it, the more energy you pour into it. So you're pulling and pulling on this rubber band, and the energy just keeps building up more and more until snap. But it doesn't break. The energy becomes so incredibly high that the universe does something amazing. It takes a shortcut. Remember E equals mc squared? Energy can become mass. Well, it becomes more energy efficient for the universe to just create new particles out of all that stored up energy. A brand new quark and an antiquark just pop into existence from the field itself. So think about that. You started with 1 particle, tried to pull a piece of it off, and you ended up with 2 whole particles instead. It's like trying to break a magnet in half and just getting 2 smaller magnets. This is quark confinement. It's a hard and fast rule of the universe. Quarks are never alone. They're always trapped inside bigger particles.
Okay, so wait a minute. If we can never ever pull a gluon or a quark out to look at it, how in the heck do we know they're even real? How do you study something you can't see?
Well, we have to look for their shadows, basically. The first clues came in the late 70s. At particle colliders, scientists were smashing things together and they saw these events where particles would spray out in 3 distinct directions, 3 jets. The math just didn't work for 2. The only thing that made sense was that a quark and an antiquark flew apart, and one of them sort of coughed up a really energetic gluon, which then created that 3rd jet of particles. It was the first time we could say, aha, there's the gluon's footprint. Nowadays, we have even cooler methods. At places like the LHC at CERN, they do something truly epic. They smash giant atoms together so hard that for a split second, they actually melt protons and neutrons. For a tiny fraction of a second, they create a drop of what the universe was like right after the Big Bang. It's called a quark-gluon plasma. And in that primordial soup, for just a moment, quarks and gluons are free. They're deconfined, and we can study how they behave in the wild. And studying that soup has led us to the gluon's biggest secret. And honestly, this might be the most important part of this whole story. It's something that completely changes how you think about, well, everything.
Okay, we've established that gluons are the glue. But what about mass? Where does the mass of things actually come from? Now you're probably thinking, I know this one, the Higgs boson. And you're kind of right. The Higgs gives fundamental particles their mass. But for the stuff that makes up our world, that's not even close to the full picture.
Just look at a proton. It's made of 3 quarks. If you add up the mass that the Higgs gives to each of those 3 quarks, you get about 1% of the proton's actual mass. 1%. So, where's the other 99%? It's not stuff, it's energy. It's the insane kinetic energy of those quarks zipping around, and here's the key part. It's the enormous potential energy locked up in that frantic, chaotic field of gluons holding them prisoner.
Let that sink in for a second. Almost all of your mass, the mass of this planet, of the sun, of everything you see, isn't from the particles themselves, it's from the energy of the glue holding them together. Your weight is almost entirely the energy of confined gluons. Mass is just condensed energy held in place by this unbreakable force. So, that just leaves us with this incredible thought, right? The strong force isn't just sticking things together. In a very real way, it is the mass of almost everything. And if this one force is responsible for something so fundamental to our reality, what other secrets is it hiding? What else are we going to learn if we find new ways to poke and prod at its extremes?
Welcome to The Explainer. Today we're going to tackle a really fundamental question about light itself. We all learned that photons are particles of light, right? But what if that whole picture, that tiny glowing bullet flying through space, what if that's just completely wrong?
Okay, so let's just jump right in and challenge that common image, because honestly, the phrase particle of light is super misleading. When you think particle, you probably picture a little dot, right? Something small stuck in one spot. But the quantum reality, well, it's a whole lot weirder.
And this right here, this really gets to the heart of it. On the one hand, you've got our comfortable idea of a particle, just a tiny dot. But on the other hand, you have this absolutely mind-bending reality that quantum mechanics points to, that a single photon, when you're not looking at it, acts more like a wave that's spread out over a huge area, maybe even the whole universe. So how can it be both? That's the puzzle we're going to unravel today.
So, to really get our heads around this strange reality, we've got to take a trip back in time, back to the early 1900s. There was this famous experiment called the photoelectric effect, and it was a total puzzle. I mean, classical physics just could not explain it. It literally forced scientists to rethink everything they thought they knew about light.
And you know what? The experiment itself is actually pretty simple. You start by giving a metal plate some extra electrons, so it has a negative charge. Easy enough. Then you just shine light on it. And the big question is this: can the energy from that light knock those electrons loose? If they manage to escape, poof, the charge is gone.
Okay, and this is where things got really, really weird. See, according to the physics of the time, classical wave theory, brighter light means more energy. Simple. So a super bright red light should have had more than enough oomph to knock an electron loose. But it didn't. No matter how bright they made that red light, absolutely nothing happened. And then they tried a weak green light, a different color, a different frequency, and boom, it freed the electrons instantly. The results were the complete opposite of what all the physics predicted, a total head-scratcher.
So, this impossible result, it totally set the stage for young Albert Einstein and his revolutionary idea back in 1905. And he didn't just, tweak the old theory. No, he came up with a completely new way of thinking about light.
What Einstein suggested was this: the energy in a light wave isn't some continuous, smooth river. Instead, he said it's quantized. Basically, it's chopped up into tiny, separate, indivisible little packets of energy. He argued that you can't just have any old amount of light energy. You can only have it in these specific chunks, these whole number multiples of a minimum energy packet.
Now, Einstein first called these little energy packets light quanta. It actually took a while, until 1926, for a chemist named Gilbert and Lewis to coin the name we all know today, the photon. And that's the formal definition, really, a single elementary packet or quantum of the electromagnetic field. And this idea leads to one of the most famous equations in all of physics, E equals h nu. All it means is that a photon's energy, the E, isn't about its brightness at all. Nope, it's directly tied to its frequency, the nu, which is just a fancy way of saying its color. So red light has a low frequency, which means its photons are these little low-energy packets. But green or blue light, they have higher frequencies, which means their individual photons pack a much bigger punch.
And just like that, this idea solves the whole photoelectric puzzle perfectly. See, the key is that an electron can only absorb the energy from one photon at a time. A single red light photon, it just doesn't have enough juice to do the job. It's too small of an energy packet. And making the red light brighter, well, that just means you're throwing more of these uselessly small packets at the electron. It doesn't change anything. But a single green light photon, now that has just enough energy in its packet to knock that electron free. It's not about the number of photons, it's about the energy in one of them.
All right, so now we can finally bring these two ideas together, right? They seem totally contradictory, the infinite wave we started with and this discrete energy packet from Einstein. But putting them together is how we get a clearer picture of the photon's true and, frankly, bizarre nature.
This gets us to a core concept in all of quantum mechanics, wave-particle duality. A photon isn't either a wave or a particle. The mind-blowing part is that it's fundamentally both all at once. The particle part is its energy that comes in those neat little packets. But its physical form, how it actually exists in space, that's a wave.
So before we measure it, a photon isn't sitting at any single point in space. It actually exists as a wave of probability, a wave that's spread out across, well, maybe the entire universe. This wave just describes all the possible places the photon could be found, but it's not actually in any of them yet. It's pure potential.
But the moment we try to measure it, the instant it hits a detector or our eyeball, something incredible happens. The very act of looking at it, of observing it, forces that huge wave of possibility to instantly collapse. It goes from being potentially everywhere to being actually somewhere.
And this is what we see. Our detector registers one single, localized hit, a dot, a particle-like event in one specific place. And that's exactly why we have this idea that photons are tiny little particles, because that's the only part we ever get to see. We're only seeing the aftermath of the collapse, not the gigantic wave that was there just a split second before.
Now, getting a handle on this bizarre quantum reality wasn't just for, academic papers. Embracing the weird nature of the photon is literally what unlocked the technologies that define the world we live in today. Think about it. This one single idea that light energy comes in these discrete packets is the foundation for so much. It's how we build lasers. It's the key to all this futuristic stuff like quantum computing and quantum cryptography. Heck, even the fiber optic cables that are probably bringing this to you right now work by controlling individual photons. It all comes back to this one amazing fundamental insight. So the next time you see a sunbeam cutting through a window, or you just flip on a light switch, remember what you're really seeing. It's not a stream of tiny little dots flying through the air. It's a vast sea of quantum waves, waves of possibility that are collapsing into reality only at the moment they hit something. It gives us a much deeper understanding of the universe, and of course, leaves us with even more incredible questions to explore.
All right, today we are diving headfirst into a real-life mystery, one that's brewing right at the heart of particle physics. It's a case that could genuinely rewrite our rulebook for the universe. And it all revolves around one tiny particle that seems to be, well, a little overweight.
And believe me, that is not an exaggeration. The question we're staring down is huge. Could one single measurement, a measurement of a particle's mass, be the clue that tells us our most successful theory of reality is wrong, or at least incomplete?
Okay, let's just get right to the numbers. On the left, you see the mass that our best theory of physics, the Standard Model, predicts for a particle called the W boson. It's about 80,357 mega-electron volts. Don't worry about the units, just think of it as its weight. Now, look to the right. That's the mass that a massive experiment at Fermilab measured back in 2022, 80,433. You can see they just don't match. And that tiny gap, less than 0.1%, is what this whole story is about.
So you might be looking at that and thinking, come on, that's a tiny difference, right? Why is everyone freaking out? Well, in the world of particle physics, precision is absolutely everything. A difference this big isn't just a rounding error, it's a potential crack in the very foundation of everything we think we know. Here's what makes it a potential bombshell: the statistics. You see,
In physics, you can't just claim a discovery. You have to reach what's called a 5 sigma level of confidence. That means there's only a 1 in 3.5 million chance your result is just a random fluke. Well, that 2022 measurement didn't just hit that mark, it blew past it. It came in at 7 sigma. The odds of that being a fluke are less than 1 in a trillion. So yeah, you kind of have to take that seriously.
So before we get any deeper into the controversy, let's properly meet the stars of our show. We're talking about the W and Z bosons, collectively known as the weak bosons.
So what are these things? Well, think of them as the delivery guys for one of the universe's 4 fundamental forces, the weak nuclear force. You know how photons carry the electromagnetic force? Well, W and Z bosons carry the weak force, and this force is responsible for some seriously important stuff, like radioactive decay and the nuclear fusion that powers our sun. They are absolutely fundamental to how the universe is put together.
And let me tell you, these are heavyweights. They are absolute behemoths in the subatomic world, weighing in at about 80 times the mass of a proton. To give you some perspective, a single one of these particles is heavier than an entire atom of iron. It's this incredible mass that actually limits the range of the weak force, making it super short range, only really acting inside the nucleus of an atom.
So what's its day job? This process, called beta decay, shows it perfectly. You start with a neutron. Deep inside, one of its down quarks suddenly flips and becomes an up quark. For that to happen, it has to spit out a W boson. And just like that, the neutron has turned into a proton, which means the atom itself has just changed from one element to another. The W boson makes that fundamental transformation of matter possible.
Okay, so now that we know what the W boson does, it all comes back to that central question. Why on earth are scientists spending decades and billions of dollars trying to weigh it so precisely? The answer is actually pretty simple. They're testing the integrity of our rulebook for the universe. And that rulebook has a name, the Standard Model of Particle Physics. It is without a doubt one of the most successful scientific theories humans have ever created. For 50 years, it has predicted the results of every experiment we've thrown at it, until maybe now.
I absolutely love this analogy from the folks at CERN. They say to think of the Standard Model as a perfect mathematical cube. The length of the sides and the angles are all defined by things like particle masses. The theory says all these measurements have to relate to each other in a very specific way to keep it a perfect cube. So if you go and measure one side, say the W boson's mass, and you find out it's a little too long, well then it's not a cube anymore, is it? It means the whole structure is warped, and something we don't know about, some new physics, must be pulling it out of shape.
And this brings us to why this is all so difficult. You can't just put a W boson on a scale. These particles only exist for an unimaginably short time, like 0.3 of a millionth of a billionth of a billionth of a second. You're literally trying to weigh a ghost before it vanishes.
To really get why it's so tough, let's look at the easy one first. Its sibling particle, the Z boson. Measuring its mass is, relatively speaking, a piece of cake. It decays into 2 particles, say 2 muons, that both fly out into your detector. You can measure them both with incredible precision. It's like measuring a wooden stick while holding both ends. It's pretty straightforward. But the W boson, oh man, that is a whole different ballgame. It decays into one particle you can see, like a muon, and one that is completely invisible, a neutrino. Neutrinos are like little phantoms. They just zip right through your entire multi-thousand-ton detector without leaving a trace. So you're forced to reconstruct the W boson's original mass with only half the information. It's like trying to measure that same stick, but you're only holding one end, and you're blindfolded. It is an unbelievably complex task.
And all of this difficulty, this mind-bending complexity, has led us to right where we are now, a scientific cliffhanger with totally conflicting evidence from different teams.
Okay, this chart right here, this is the whole drama in one picture. That first bar on the left is the prediction from the Standard Model, our baseline. The middle bar, that's the 2022 result from the CDF experiment. You can see it's way higher. That's our overweight particle. But then, and this is the big but, look at the bar on the right. That's a newer result from 2023 from a different experiment called Atlas, and it landed almost exactly where the Standard Model said it would. So now we have 2 of the best experiments in the world in direct public disagreement.
And you can see from this timeline just how wild the last couple of years have been. After the particles were discovered way back in '83, things were chugging along. Then, boom, the 2022 bombshell from CDF.
Just a year later, Atlas fires back with a result that says, nope, the theory looks fine to us. And then, just this year, the official group that averages all these results basically sided with Atlas, excluding the CDF measurement and calling it an outlier. The plot just keeps getting thicker.
So, where does all this leave us? Well, we're in this amazing, fascinating moment of scientific suspense. The case isn't closed, and physicists all over the world are on the edge of their seats waiting for the final verdict.
When you boil it all down, there are really only two ways this can go. Possibility one. The CDF team, as brilliant as they are, made a mistake. There's some tiny systematic error hidden in their analysis, and the standard model is safe. Possibility two. The CDF measurement is correct. If that's true, it is a Nobel Prize-winning discovery. It would mean the standard model is incomplete, and some new undiscovered particles or forces are out there, messing with the W boson's mass. This could be the key to unlocking bigger mysteries like what dark matter is. It would change our map of reality.
And that leaves us with a million-dollar question that physicists are now racing to answer. Are we looking at an honest mistake made by brilliant scientists pushing measurement to its absolute limit? Or are we seeing the very first tantalizing glimpse of a whole new universe of physics we never knew existed? Right now, nobody knows for sure. And that, right there, is what makes science so incredibly exciting.
Today, we're going to talk about a discovery that honestly fixed a huge flaw in how we thought the universe worked. We're diving into the Higgs boson and the story of how it solved a puzzle that gets to the very heart of why anything, well, is anything at all. All right, so let's jump right in. For decades, physicists were staring at this massive puzzle. I mean, think about it. If the basic rules of the universe apply to everything, then how come some fundamental particles have mass, but others, like the photon, a particle of light, have absolutely none? This wasn't just a small issue, it was a huge crack in the very foundation of physics.
So, just how big of a deal was this? Well, to really wrap your head around it, you have to look at what was considered the rule book for the entire universe. It was this beautiful theory that was almost perfect, except for this one glaring, universe-sized flaw.
You see, physicists had this amazing theory called the Standard Model of Particle Physics, and it was, for lack of a better word, a triumph. It described pretty much every particle and force we had ever seen with just jaw-dropping accuracy. But for all that success, there was this massive, gaping hole right in the middle of it.
And here's where things just completely fell apart. The math, the very core of the Standard Model, was totally clear. Certain particles, the W and Z bosons, which carry one of the universe's fundamental forces, they had to have zero mass. But then we go and find them in experiments and, nope, they're incredibly heavy. Some of the heaviest particles we know. This wasn't some tiny rounding error. The theory was broken. Seriously, physicists just called it the central problem in particle physics. That's how bad it was.
So, how do you fix a problem like that? Well, the solution, which was dreamed up way back in 1964, wasn't just a little patch. Oh no, it was this totally radical new idea that basically changed everything we thought we knew about empty space itself.
What they proposed was that empty space isn't empty. Not at all. They imagined that the entire universe is filled with this invisible energy field. Think of it like a hidden ingredient, a cosmic molasses that permeates everything. And its one job? To give particles their mass.
And this is the really mind-bending part. The big takeaway is that mass isn't something a particle just has, you know? It's not some built-in property. Instead, a particle gets its mass from how much it interacts with this field, the field we now call the Higgs field.
Okay, here's a great way to picture this. Imagine the Higgs field is a giant swimming pool that fills the whole universe. Now, some particles, like photons, are like super sleek professional swimmers. They just zip right through the water with barely any resistance, so they stay massless. But other particles, like the top quark, are, well, let's just say they're not so streamlined. They interact with the water a ton, and all that resistance, that drag, that's what we experience as mass.
But, you know, an invisible field is just a cool idea until you can prove it's real. So how in the world do you do that? Well, the theory made this one crucial prediction. If you could smack this field with a huge amount of energy, you could actually make it ripple. And that tiny ripple, a quantum excitation, would pop into existence as a particle. And that particle, that was the Higgs boson. Finding it wasn't just a clue. It was the smoking gun.
Finding that smoking gun, though,
That was going to be tough. In fact, it kicked off one of the longest, most expensive, and most ridiculously complex scientific hunts in the history of humankind.
I mean, this wasn't a weekend project. This hunt spanned generations of scientists. We're talking more than 40 years, starting from when the idea was just on paper back in the 60s. Physicists just kept building bigger and more powerful machines, one after the other. First at CERN in the 90s, then at Fermilab in the States, each one pushing the limits of technology, all to find this one single, incredibly elusive particle. And the whole quest basically led to the creation of the Large Hadron Collider, the biggest and most complex machine ever built by humans, period. And the scale of what they were doing, it's just hard to even get your head around. At the LHC, scientists had to analyze the data from over 300 trillion individual proton-proton collisions. 300 trillion. Imagine trying to find one very specific grain of sand on every single beach on Earth. That's the kind of odds they were up against, hoping to spot that 1 in a billion event that screamed Higgs boson.
And then, after all those decades of searching, after thousands of scientists poured their lives into this, after billions of dollars were spent, the moment finally came.
It was July 4th, 2012. Picture this, a packed auditorium in Geneva. The leaders from two completely separate giant experiments at the LHC, they're called ATLAS and CMS. They get up and announce that they have both found a new particle. The place just went wild. It was an incredible moment.
So what did they find? They found a new boson, a new type of particle, with a mass of about 125 giga-electron volts, which is pretty hefty. But the real headline was the statistical significance. They hit what's called 5 sigma. Now, in particle physics, that's the gold standard for a discovery. It basically means there's less than a 1 in 3 million chance that what they saw was just a random fluke. This thing was real.
Now, they still had to be sure. It took another 8 months of just grinding through the data, checking and double-checking everything. But by March 2013, the verdict was in. The evidence was undeniable. CERN officially confirmed it. The new particle was, indeed, a Higgs boson.
So, the big question is, why does this matter so much? What's the big deal? Well, finding the Higgs wasn't just about ticking a box on some old theory. No, this discovery fundamentally changed how we see the entire universe.
Just think about everything this one discovery did. First, it proved that the Standard Model, our best theory for how the universe works, was actually correct. It finally gave us the how for mass, confirming that invisible Higgs field is real. And on top of all that, the Higgs itself was a totally new kind of particle. It's a scalar particle, which means it has no spin, and that's something we'd never seen before in nature. It completely opened up a new chapter in physics.
But here's a really cool twist, something that might surprise you. The Higgs field isn't actually responsible for most of the mass that makes you you. In fact, for the protons and neutrons in your body, only about 1% of their mass comes from interacting with the Higgs. The other 99%? That actually comes from the incredible amount of energy that's binding the tiny quarks together inside them. So mass is way more complicated and, honestly, more amazing than you'd think.
So, finding the Higgs boson answered one of the biggest questions in physics. But in a classic twist, it also raised a new, and honestly much more unsettling question. See, the very specific mass of the Higgs that they found, it hints that our universe might not be truly stable. It might be in what physicists call a false vacuum, like a ball resting in a small dip on a hillside, instead of all the way at the bottom. The terrifying implication is that someday, maybe billions of years from now, it could suddenly roll down to the true bottom, collapsing into a totally new kind of reality, and wiping out everything we know in an instant. So it leaves us with this one final, pretty chilling thought. Did the discovery of the Higgs boson reveal that our entire universe is living on borrowed time?